Ladies and gentlemen, learners and seekers, welcome to Learning Academy Foundation from Mr. Andrea. Today, we journey into the quiet architecture of logic, the fundamentals of algorithms. Not just lines of code, but patterns of thought. Not just instructions, but reflection of how we solve, simplify, and serve. Let's begin with the representation of algorithms. An algorithm is a set of steps. Experiment, design, analyze, implement. A recipe for solving a problem. We can represent it in many ways. Through natural language, though it risks ambiguity. So natural language processing is divided in a natural language understanding, comprehending what is being said. For example, what's your return policy? Machine learning, determining the right response, and the natural language generation, giving a response in human-like format. For example, you can return your item within 30 days of receipt. Through pseudocode, which balances clarity and structure. Clarity is a primary goal of pseudocode, and it may help if you work within accepted programming conventions. As you develop your pseudocode into actual code, you will need to transcribe it into a programming language. So it can help to structure your outline with this in mind. And then flowcharts. Visual maps that guide the eye and mind. But before we write, we must decompose. What is decomposition? Composition is the process, the art of breaking down a complex problem into smaller, manageable parts. Like a mosaic, each tile matters. Like a symphony, each note plays its role. We ask, what are the sub-problems? What can be solved independently? Then comes abstraction. In the world of computer science, we call this abstraction, a mental tool that allows us to ignore low-level details when they are unnecessary. So it is the sacred act of hiding unnecessary detail. We don't need to know how the keyboard works to read input. We don't need to see the wires to trust the signal. So this ability to ignore small details is what allows us to develop complex encodings and protocols. Abstraction lets us focus on what matters. It's the difference between knowing the forest and counting every leaf. Now, let's talk about input and output. Input devices is how a program listens. Through the mouse, that is a pointing device that functions by detecting two-dimensional motion relative to its supporting surface. Physically, a mouse consists of an object held under one of the user's hands with one or more buttons. The keyboard is still the commonest way of entering information into a computer. The tracker balls, it is an alternative to the traditional mouse and often used by graphic designers. The sensors. Output is how it speaks through the screen, the sound, the printed page. Together, they form a dialogue between human and machine. We ask the user, for example, what's your name? And the algorithm responds. But how do we know what an algorithm truly does? We use trace tables and visual inspection. What is a trace table? A trace table is a method of testing an algorithm to ensure that it works as intended. So using a test table, it is possible to identify any potential logic errors that need to be amended. A trace table records the changes that take place to data within an algorithm. Changes most commonly take place within variables and outputted information. The table header will include all the variable values within the algorithm. When using a trace table, you input data from left to right, top row to bottom row. We walk through the steps, line by line, recording values, watching variables change. There are two types of variables: independent, that is the one that change. For example, in watering plants, the independent variable is the amount of water we can change. We can decide how much water, how many liters to water the plant. And the dependent variable that is affected by the change. So it's like the consequence of the change. For example, the size of plant, the number of leaves, if it's still living or dead. So you can think as the independent variable as the effect and the dependent variable as the consequence. We become detectives of logic, tracing the footprint of computation. And then we ask, is this the best way? We compare the efficiency of algorithms. Some are fast, some are slow, some scale well, others stumble. We measure time and space. How long it takes, how much memory it needs. Efficiency isn't just about speed. It's about wisdom. It's about stewardship. It's using the least amount of inputs to achieve the highest amount of output. Let's meet a few familiar faces in the algorithm family. Linear search. A humble wanderer checking each item one by one. Binary search. A strategist dividing and conquering, but only when the list is sorted. So in a set of numbers, we will see which one is the lowest, in this case 11, which one is the median, in this case 45, and which one is the highest, in this case 95. We want to search for 50. The median is 45, so 50 is greater than 45. So we eliminate the first half and take the second half. The second half, this position 4th, 5th, and 6th position, right? Which one is the lowest number is 50. Which one is the median is 71. Which one is the highest is 95. All right. So the median is 71. So the 50 is less than 71. So we take the first half, and we found 50 at the position 4, and then it's done. This is how binary search works. By searching the media and then comparing the data that we want, the number that we want, with the median, eliminating the other half that we don't need. Then bubble sort. So this is how to. There are two types of sorting. Bubble sort, that is a gentle sorter, swapping neighbors until the order merges. Okay, for example, we have 6, 2, 8, 4, 10. 8 and 4. We know that 8 is greater than 4, so it should go to the right. And 4 is smaller, so it should go to the left. So we shift. This is the next pass, the second pass. The third pass, we have 2, 6, 4, 8, 10. 6 is greater than 4. 4 is smaller than 6, so they have to shift. So 2, 4, 6, 8, 10. Is it in order in correct ascending order? Yes. So this one is how to bubble sort works. And the other type of sort is merge sort. So we have, this is a master of divide and conquer, elegant and efficient. The first section is divide. So we have 8, 7, 4, 2, 9, 1, 5, 6. There are 8 numbers, right? So we can divide in 2. One on the left, 8, 7, 4, 2. On the right, 9, 1, 5, 6. And then we divide again 2 by 2. So one group is 8, 7, one group is 4, 2, one group is 9, 1, one group is 5, 6. This one can be divided again by 2. So 8, 7, 4, 2, 9, 1, 5, 6. And then 8, 7, which one is smaller? 8, 7, right? So we put 7 on the left and 8 is greatest on the right. 4, 2, which one is smaller? 2, 4. 9, 1, which one is smaller? 1. So put 1 on the left and 9 on the right. It is bigger. 5, this is conquering. Okay? Conquering. So 5, 6, they are already in order. 5, 6. Then 28, 24. Which one is smaller? 24. So 24 goes to the left. 78 is greater, so 78 goes to the right. 1956. So first number is 1, and then 5, and then 6, and then 9. Now we have 1, 2, 4, 7, 8, 1, 5, 6, 9. We put in order 1, 2, 4, 5, 6, 7, 8, 9. This is how it works, how merge sort works. So each has its place. Each teaches us something about patience, precision, and purpose. And now let us pause and reflect. In the structure of algorithm, I see echoes of divine design. God too decomposes our chaos into grace. In 2 Corinthians 12:9 we can read, "My grace is sufficient for you, for my power is made perfect in weakness." He abstracts our flaws, seeing the hurt beneath the error. He inputs our prayers and outputs peace. He traces our steps not with tables, but with mercy, and his efficiency perfect, timeless, unbounded. In Psalm 139, from 1 to 6, we read, "You have searched me, Lord, and you know me. You know when I sit and when I rise. You perceive my thoughts from afar. You discern my going out and my laying down. You are familiar with all my ways. Before a word is on my tongue, you, Lord, know it completely. You hem me in behind and before, and you lay your hand upon me. Such knowledge is too wonderful for me, too lofty for me to attain." Is that not the ultimate trace table? Is that not the most loving algorithm? So as we code, let us also care. As we sort, let us also serve. As for me and my household, we will serve the Lord. As we search, let us also seek the kingdom of God. For every algorithm we teach, may we also teach compassion, kindness, and confidence. For every output we display, may we also display truth, and for every input we receive, may we respond with love. Thank you for your attention. See you next video. Bye.